in algebraic geometry. And when you think about it, if you have a group acting on a set, what you call the quotient is just the set of G orbits. And since you're working with sets, you're totally happy. Now it gets a little more interesting when you go into the world of topology, because then I'll have a topological space, I'll have a topological group acting on the space in a continuous way. I still have a set of G orbits, and I even have a topology. It's called the quotient topology. And if you take the map that sends a point to its corresponding orbit, call that pi, then what you do is use the quotient topology. And what that simply means is that a set, sorry, what does it mean for a set here to be open? You declare it be open if and only if pi inverse of u is open back in X. So you have a very nice topology, and this makes this into a continuous map. But it turns out that this is where you begin to see there are problems. For example, the orbits now are taking place in X, and so the orbits are now subsets of a topological space. And in particular, if there's a non-closed orbit, then your quotient can't be Hausdorff. And that's actually one of the problems that one of the groups are going to work on tomorrow. So even in the topological case, you can run into, so you can basically go from you can have a beautiful Hausdorff space, but if you have a non-closed orbit, your quotient space is just not going to be very nice. And so the question is, what do you do in algebraic geometry? Because then you have a variety, you have an algebraic group. What on earth is the quotient? And just to give you a preview that yes, there are many problems when you try to do this. And so to get started, let's talk about the affine case. Because there I have X equals spec R. And so here, this is going to be now an affine variety. So, R will be some finitely generated algebra. We're working over the complex numbers. And then the way to think about stuff is, so I have this, I'll put quotation marks because I don't quite know what it is yet. The idea is I want to have a quotient, and I want to have a universal property. And the universal property is what happens when I map to other things. And of course, here's the point, is when I take the quotient, basically all things in the same orbit should map to the same thing here. And so when I map to another space, what that's really meaning, what's really going on is I'm looking for functions that are constant on G orbits. And to have a good notion of a quotient, if I have a function here, or a morphism that's constant on G orbits, it should factor through the quotient. So that's the kind of universal property that we want. This is sort of what you would call a categorical quotient. And now it turns out that if Y is also affine, then what this diagram turns into is, so here's R, here's S. This goes the other way. But the point is that the elements of S, well, basically, since this map is constant on G orbits, these will map, and these are basically the functions on X. These map to G invariant functions on X. And of course, that's just the ring of invariance. So in fact, we actually, at the level of rings, we know how to fill in this diagram. The thing that goes here is just because basically if G acts on this affine variety, then it'll also act on R, and I just look at the ring of the subring of invariance. And so, and of course, also part of the idea about affine varieties is you know an affine variety by knowing its functions. And so, what that says is, oh, my quotient should be the ring of invariance. Now here's the first of many problems that crop up. So the immediate problem is, remember, I want to be in the land of varieties. So I want all my rings to be finitely generated C algebras. But the point is that the ring of invariance need not be a finitely generated C algebra. And this is actually related to Hilbert's 14th problem. And this is, from the modern perspective, this is why a lot of the invariant theory done in the 19th century is important, because they were actually trying to figure out these rings of invariance. It turns out that there's a partial solution. And the idea is that what happens is that if I allow G to be an arbitrary algebraic group, there really are nice counterexamples. But if I put some restrictions on G, and then we're fine. So it turns out that the ring of invariance is finitely generated. And that's true when G is reductive. So this is from the language of algebraic groups. And a group is reductive. That means that the maximal connected solvable subgroup is a torus. And so let me give you two examples of reductive groups. A torus is very definitely, it's abelian, so it's solvable, and the torus itself is the maximal thing, and tori are connected. So a torus is reductive. So that's, for our point of view, that's really important. But another one is a finite group, because of course a finite group, the maximal connected subgroup has to be just trivial, and that is a zero-dimensional torus. So here are two classes of groups where this works. And so then the question is, so there's really two questions, and the first question is, how close is spec? So when I look at spec of the ring invariance, how close is that to the set of G orbits? And we will see they're not always equal. So that's the first thing. And then the second question is, how do we do this in the general case? So what happens when we're in the non-affine case? And so I'm going to give you partial answers to both of these. And the answers will involve basically 3 definitions, 5 examples, and a couple of theorems. So 3 definitions, 5 examples, and some theorems. And all of this is section 5.0. And so the first definition is, I'm going to define what's called the geometric quotient. This is going to be the nicest of the bunch. And an example of a geometric quotient is going to be, for example, when you construct projective space. Or when you do our lattice change game, where you have the finite index, and then remember we talked about how this was a quotient where G is n prime mod n. So we've already talked about this example. That's, of course, projective space. Both of those quotients genuinely are wonderful geometric quotients. But that's not all the quotients we're going to deal with. The second thing that happens is somebody, well, he's almost a geometric quotient. And so we will very cleverly call it an almost geometric quotient. And so this is example A. This is example B. So an almost geometric quotient is, and also there's some notation I'm going to introduce, because I want to use a quotient notation, but you know, this guy is not the actual quotient, and so we typically will use sort of, instead of 1 slash, we'll use 2 slashes to indicate that we're not quite a geometric quotient. And I need to tell you what the action is. The action is the T times A, B, C, D. Basically, it maps the first 2 just by T, and the second 2 it maps by T inverse. And so here are the examples. That's A, that's example B. This is going to be example C. But then there are actually things that actually aren't almost geometric quotients that still crop up. And so that's called a good categorical quotient. So that's going to be the third definition. And an example of that is I just take, say, Cn plus 1. So I basically take this example and stick the origin back in. And we will see that a good categorical quotient actually exists and has appropriate universal properties. That's going to be D. But also, one thing is that we can actually have quotients that are non-separated. And that's sort of vaguely similar to this, because remember, separated is sort of the algebraic analog of Hausdorff, but it's sort of even more evil than that. So, and in fact, this is so evil, we're not going to even say it exists. And yet, you can write down really simple examples, because you can write down C2 minus the origin going to mod out by C star. It's looking pretty harmless, but I'm not going to use the usual action. I'm going to use a slightly different one, that T times AB is going to be TA, but T inverse B. And it turns out that the quotient that you get out of this case is actually a non-separated variety. So let me start with definition 3. So G acts on X, and again, algebraic variety, algebraic group, algebraic action, I'm always going to be saying that. And then the quotient, I'm not going to give it a name at this point. So the quotient, I'm just going to say Y. So what does it mean to say, and notice that this is the good categorical quotient that I'm defining. So what does it mean to say that this is a good categorical quotient? And so it's a morphism of separated varieties. So in particular, the definition I give here is actually going to exclude this example. And it's basically, so again, that's good categorical quotient. It's a fairly long list of stuff you want to happen. And so first of all, you want pi to be constant on G orbits. So that's pretty obvious for a quotient. And I want to capture this idea of invariance. So how do I do that? And the answer is that suppose I take an open set downstairs, then I can look at the functions downstairs, but I can also pull this upstairs, so I can go look at OX pi inverse of U. Now notice that since pi is constant on G orbits, G acts on this, and so I can take its ring of invariance, and again, because this map right here is constant on, since pi is constant on G orbits, there's actually an inclusion here, and I actually want an equality. And that's really capturing this idea of saying that, in the affine case, the quotient is just the functions, the ring of invariance. So this is sort of a globalization or a sheafification of that. So that's pretty obvious. And then there's a couple of more things, and this is just what people over the years have figured out they need to make things work. Suppose that I have something in X, so now I have something upstairs that's G invariant and closed. Then in that case, when I push it downstairs, it remains closed. And then another one that you want let's take two closed disjoint G invariant sets. Then what happens is I want their images downstairs also to be closed, or to be disjoint. And you might say, isn't that obvious? And the answer is no, because I'm not assuming that this is a set of G orbits. And so, I'm just trying to, come up with something that works. And so it turns out, so here's our first theorem. In fact, I'm going to give you two theorems. About good categorical quotients. So again, I have X, I have the algebraic group acting on it, and all that good stuff. And so the first is, it really is a categorical quotient. So here's our friend pi, and then suppose I have some other variety, and I have a morphism that's constant on G orbits, then it factors through. So it really does have the correct universal property, and this is really what you call a categorical quotient. The second thing, which is not obvious from the statement, but it turns out this morphism, if it's a good categorical quotient, it's actually surjective. And the third one is that it actually has this property. The topology is actually the thing you would want. And so U contained in Y is open if and only if pi inverse of U contained in X is open. And of course, one direction is obvious because morphisms are continuous in the Zariski topology, and so it's the other direction. If I have something here and if upstairs I get something open, then I've got something open downstairs. And then the fourth is our first hint that this might not quite be the space of G orbits. Because suppose I take 2 points in X, then where do they have the same images? Well, of course, in this naive setting, they have the same image if and only if they give the same G orbit. And the answer is it's not true in this case. What it is so that's the G orbit of X, that's the G orbit of Y, and they give the same image if and only if their orbit closures intersect in X. So this again is the fact that orbits might not be closed. And because notice that if I take away the closure, then just saying the orbits intersect, that means they've got to be equal. And but we'll see some examples where the orbits actually are disjoint, but the orbit closures have something in common. What? Oh yeah, that's right. There's a not. Thank you. And so that's one theorem. Another theorem is that if my variety is spec R and G is reductive, then the map, I get an inclusion here. And again, since that's reductive, that's our nice finitely generated G algebra, and I get a map on spec going the other direction. And the point is, this is a good categorical quotient. And so in the affine case, when you have a reductive group, then taking the quotient gives you something good. And so, for example, that's what this is. Because here's an affine space. Here's a reductive group acting. So this is actually going to be, this is actually definitely a good categorical quotient. Here's another one. Here's affine space with stuff. So both of these are good categorical quotients. We will see this one is much nicer than that one. And then the notation is I'm going to write a good categorical quotient as pi mapping x to, and so I'm now formally introducing this notation. So this says that I'm in a situation where the good categorical quotient exists, and it's equal to that. Okay. Whoa, ho, ho. Thank you. So now let's do an example. So let's actually do example D. And the bottom line is that in spite of the pretty name, a good categorical quotient, some of them are actually pretty bad. And so let's compute. So let's compute this one. Well, this is the affine case, and so this is the ring of just polynomials, and this is just the usual action of C star, where I multiply all the variables by a constant. And now if I take any polynomial in here, then I can write it as a sum of homogeneous polynomials of degree k. And then, of course, when I plug in lambda here. And again, this x stands for the vector of all the variables. Here I'm multiplying all the variables by lambda. These are homogeneous to degree k. And so I just get lambda to the k times fk of x. And the question is, when is that equal to the polynomial I started with? Because that's what it means to be invariant. So I take my polynomial, do this, I get this. I've got all these lambda to the k's there, and yet that's supposed to be just f. Turns out there's only one way to avoid embarrassment. So what polynomial am I? I've got to be the constant polynomial. So in fact, yes, this is a good categorical quotient. The quotient is a point. Now that, so what that says is that, my God, something terrible is happening, because that's dimension n plus 1. I'm modding out by a one-dimensional group. You'd sort of say, hey, isn't the quotient got dimension n? No, the answer is quotient's got dimension 0. So that's the problem. These guys can be really bad. And I can actually explain why, and the why really comes from this fact right here. So let me explain why. By the way, definitely ask questions if you have any. So it turns out, that's sort of the algebraic, what's here is the algebraic reason why the quotient is is just a point. Now, what's the geometric reason? Well, let's take any old point in Cn, and let's take its orbit and take its orbit closure. There's really only two possible cases. One is I get the line through the origin, and what condition does V have to satisfy for that to happen? It's not true for all V. It has to be non-zero. And then, of course, as V is 0, that's the fixed point, and I get that. But notice that in all of the cases, 0 is contained in C star, is contained in the orbit closure. So every single orbit, 0 is in the orbit closure. So every x and y, the orbits meet at the origin. That means that every x and y map to the same thing. And the map is surjective. I am talking about a point. So you can really begin to see why, this really works the way it does. Okay, so that's that. But now it's time to, so that's sort of the worst case scenario. And like I say, that's why, I put, that's really a good categorical quotient, just sort of barely. Now let's talk about the best case scenario, which is the geometric quotient. So that's just going to be a slight variation on this. So here, this is definition 1, and so this is the geometric quotient. So this is the one we really like. So let's take a good categorical quotient. There's two equivalent things that can happen. So the first is that all G orbits in X are closed. And that's sort of we've already seen closed orbits are a good thing, and so that's really nice. And notice that means in this condition, if the orbits are closed, I can dispense with that. So in fact, we discover that two things map to the same thing only if they lie in the same orbit. So in fact, what we get, this condition is actually equivalent to saying that the set of G orbits there's a bijection to this. And so notice now we've actually taken the set of G orbits and we've turned it into a variety. So that's what a geometric quotient does, is it takes this sort of naive set. So when I have a geometric quotient, I turn this into an actual variety. And so that's a geometric quotient. And example B, and it turns out that it's written X mod G. And then so we write just the single one to indicate we've actually got a geometric quotient. And of course, example B, which I had on the board earlier, is that when I take Yeah, I'm sorry. In fact, I messed this up. You're supposed to yell at me, but you're probably brain dead like I am because it's been a long day. Because usually when I write this, n prime maps to n, so it goes there. My apologies. So in this case, when we were talking about this, this is a geometric quotient. And so that notation that I used, and because notice that this naively really reflects just the set of G orbits. So this is, naively this is a set. How do you give that set the structure of a variety? That's what gives it the set of structure of a variety. So this is a very nice geometric quotient. So that's pretty good. Now let's do an example where we move into the land of non-affine things. So now let's do example A. Because that'll give you an idea about how you actually do this stuff in general. So what I do is, so see, I have a pretty good idea about what to do in the affine case. So what do I do in this non-affine case? Well, the answer is I cover it with affine opens that are invariant under the group action. And then I do my game for each one of those. And of course, what are the what's a nice open cover of invariant affine opens? That's just the standard open sets. I'll call it UXI, where xi is not equal to 0. And the point is that this is a C star invariant affine variety. And then if I take UXI and mod out by C star, well, it's sort of the same kind of argument that I did when I was doing here, except that I've now got a little more freedom because there I just had polynomials, but now you see I can have xi as a denominator. And that's what saves it. That's what actually gives me something more than just the constants. And so, in fact, what you can check and so this is C of so let's see. So how do I want to say this? So what I'm going to do, so how do I get that set? So I take x naught to xn. Because remember, this is upstairs. So in fact, you have to be slightly careful because these are not the open cover of projective space. This is an open cover of affine space. So, or rather, of affine space minus the origin. So in this case, this is really sitting inside of here, so I'm really just taking this ring and just inverting xi. Now that basically allows all sorts of stuff, but then I have to take the invariance. And what made this argument over here work is that the reason I got C was because that's the stuff of degree 0, because that's the stuff that's invariant. And so I similarly take the stuff here of degree 0. That's what's going to be invariant. But what's nice is that, well, how do I get the stuff of degree 0? And the answer is I take quotients of the variables. And the point is the denominator I'm allowed is xi. So you take x naught over xi, xi over xi. And of course, that's just 1, xn over xi. And so what we get is just, I get the Cn. And so there, when I So I basically take the variety, write it as a bunch of C star invariant affine opens. Then I take the quotient on each one of these. And then, of course, I have to glue them together. But it turns out the gluing is fairly automatic because these are categorical quotients. So that guarantees that everything just fits together. And so the fact that this is a, this is a good categorical quotient implied that things patch. And they patch in the usual way. To get Pn. And so that's how you try to form one of these quotients. In the general cases, you take your variety that's not affine. If you can find invariant affine open subsets, then you can take the quotient, patch, and you get what you want. So that's really nice. And then what's interesting is that notice that the orbits in Cn plus 1 minus 0, well, remember that when I was talking about just all of Cn, when I sort of, here I sort of got the non-zero points on the line, and then I had to close it up, I had to add the origin. But now I've removed the origin, and the point is that when I take C star dot V, where that's not 0, the point is this is closed in that set because I've removed 0. So all my orbits are closed. Therefore, it's a geometric quotient. So that's pretty nice. Now the next thing I want to talk about is, so here you see in the case of a geometric quotient, I really understand what this is, because it really is just a set of G orbits. So what about in the more general case? So I want to give you one other theorem. And this is the geometric meaning of a good categorical quotient. So what's happening here so again we have our setup, and we're back to the double bars because it's just a good categorical quotient, and then pi induces a bijection because you see in this case I had a bijection between the geometric quotient and just the G orbits. Of course the G orbits are all closed. What happens is that in the general case of a good categorical quotient, what we get is simply the closed G orbits. So that's a really nice theorem. And for example, in this setting, notice that the orbits so, and again, when I let C star act on all of Cn plus 1, so basically our, this one right here, you see that the orbit, notice that that's not closed. So how many closed orbits do I have? Exactly one, the origin. That's why, so there's exactly one closed orbit. That's another way to see, in this case, that the quotient is just a single point, because I have a single closed orbit. So we're making progress. This is looking really beautiful. But there are icky things out there. So time to talk about just how complicated things can actually get. So let's see. I'll do it here. So I'm going to take something that looks pretty harmless, and so let's do example E. So just this guy. And so first of all, let me give a very naive reason and again, let me just write down my action again just to make sure. So it, first multiplies by t, the second coordinate multiplies by t inverse. So why is that bad? Well, so what do the orbits look like? And here, let me work over the real numbers. So what the orbits look like, well, notice that when I do this, the one thing that's unchanged is the product of the coordinates, because I get a t there and a t inverse there. So in fact, the orbits, most of the orbits are actually hyperbolas. So here's xy equals a. Here's the case where a is positive. And there would be xy equals a, where a is negative. But that's not the only orbits. What's another orbit? And remember, I've removed the origin. So there's two more orbits. What are they? Yeah, the axes. So the x-axis minus the origin, the y-axis minus the origin. Now the question is, what does the quotient look like? The quotient is one-dimensional. And one way to think about it is that, and again, I'm sort of thinking over the real numbers. So when a is positive, basically it's just the a that tells me what the orbit is when a is positive. And so I get all this. And then, of course, when a is negative, that's sort of these orbits. And that basically captures everything except that I have these two orbits. And how do they fit together? Well, think of a approaching 0 through the positive numbers. So right now, here I've sort of drawn a picture, and I'm sort of reserving judgment for what happens at 0. So when a is positive, I know what the orbits look like. When a is negative, I know what the orbits look like. But when a is 0, how many orbits are there? So what is xy equals 0? So that's the x-axis and the y. So all of a sudden there are two orbits, and they're different. And furthermore, notice that, like if I try to think topologically, imagine a point here, which is this orbit. Imagine that trying to approach 0, and notice that. So here's a sequence of points. It has two limit points simultaneously. And so what we've got, of course, is our non-Hausdorff space right here. And so it's clear we have something bad going on. And now let's do a more careful version. And so I'm going to play the same game that I did here. I'm going to take my space and write it as a bunch of invariant affines. Question?
Yeah, I just mean how can you retrieve the algebraic action form? If this is just a Fourier action form, right? Then set theoretical.
So
yeah, so this action is given by the set theoretical form, right?
Yeah, so this is the action.
Yeah, but how can you retrieve this to an algebraic action form?
This is an algebraic action. I mean, this is a morphism from C star cross C2 minus 0 to C2 minus 0. T, a point here, T, a point AB here, goes to that point there. That's a morphism of varieties.
Yeah, but like, so if you want to find the ring of invariance.
Well, remember, this isn't affine. See, I can only do the ring of invariance case in the affine system. So to do what you want to do, I have to cover this with affine opens. See, like right here, like in this case, I can't take the ring of invariance. I have to work locally, take the ring of invariance locally, get a quotient and glue them together. And I'm going to do the exact same thing here. And the point is that so here I'm going to write it just as Ux union Uy. And I'm going to think geometrically about it, but you can also do it algebraically. If I think geometrically, well, see what this guarantees is I have points where the first coordinate is non-zero. So that's what Ux means. The first coordinate is non-zero. So I can use the group action to make the first coordinate 1. And then the second coordinate is just going to be some complex number. And of course, it can't be 0 because, I've removed the origin. Well, actually, because it's 1, it actually could be. Yeah. So in fact, in this case, it's a copy of C. And then I play the same game here. But now the second coordinate is non-zero. So again, by picking an appropriate T, I can make the second coordinate 1. It's a copy of C. How do I glue these? And so, but the point is that a complex number C, so basically, so that's a point in the quotient. So I give 1C here, and so that's in one quotient. And then it also gives C1 in the other. But it turns out these points are equivalent. Because what is C times 1C? If I multiply the first coordinate by C, the second by C inverse. So if C is in C star, then this is just C1. So in fact, what I've got here is precisely the example I gave you the other day, that I simply have two copies of the complex number. Here's one copy of the complex numbers. Here's another copy of the complex numbers. And my group action basically says when my little c is in C star, identify them, but identify the C here to the C there. So identify the exact same point, and so this actually gives me that guy on the nose. And so in fact, that non-separated variety that I showed you is exactly this quotient. And yet what I did here is achingly close to what I did here. So that's why I don't work on group actions, because they're really subtle and difficult. That you can do something that here gives you a beautiful variety, and here I make the tiniest tweak, and it's sort of nonsense. And so that's one thing we got to be careful about when I talk about quotients tomorrow, I got to make, basically, somewhere you got to make sure that, hey, this quotient is actually a separated actual variety that we like and not some weirdo thing like this. Okay, so let me do, the example I haven't done yet is C. So I'm actually pretty close to being done. So I want to do example C. That's this one. And then I want to tell you what an almost geometric quotient is, because that's going to be something that's pretty important for us tomorrow. An example C is one that's also on one of the exercises that some of the groups are going to do tomorrow. And so I'm going to skip some of the details. So this is actually an affine example. And that's going to mean that we can just take a ring of invariants, so we don't have to worry about any of this open cover stuff. And so I have 4 variables. I'll call them x1, x2, x3, x4. And so can you tell me something that's invariant? Yeah, so basically x1, x3. Because I multiply that by that, and the t's cancel. And in a similar way, x2, x4 is that. And then you also get, for example, x1, x4, because again, that's a t and a t inverse. And the final one is x2, x3. And if I call this x, y, z, w, what's the relation between x, y, and zw? Yeah, x, y equals zw. And so this is, so the ring is, now I'll switch to little lowercase variables. So what that says is that, so what we've shown is that when I look at C4 and I take the good geometric quotient by C star, we get our favorite toric variety, xy minus zw. And tomorrow when I talk about the quotient construction of toric varieties, this is going to be the quotient construction of this toric variety. Now what's interesting is that it's got some awkward behavior. It's got some good behavior and some not so good behavior. So let's talk about the good stuff. And then we'll talk about the stuff that's a little more complicated. I'm going to let, so what I'm going to do is here, because notice, so what's the most singular point of this variety? It's going to be the origin. So let's remove the origin. So I'm removing one point. And then there's 2 interesting observations. Pi inverse of 0. Now, remember if this was a geometric quotient, points here would correspond to orbits. And so if this were a geometric quotient, this inverse image would be a just a single orbit. But what you can work out is that, what I'm saying is, what's the variety defined by setting all of those equal to 0 simultaneously? x1 equals 0 or x3 equals 0, x2 equals 0 or x4 equals 0. Then you sort out what's going on and you discover that either the last two coordinates are 0, so that's x3 and x4, because basically everybody contains an x3 or an x4. So when x3 and x4 are 0, everything vanishes. And then what's another way to make everybody vanish? Yeah, x1, x2. And it turns out that that's pretty much the whole thing. And it turns out that this is in C4, and this is a union of infinitely many orbits. In fact, one thing you'll work out in one of the exercises tomorrow is, yes, there are infinitely many orbits, exactly one of which is closed. And so you really get to, and so again, that's the idea, is that a geometric, sort of this geometric quotient, it has trouble seeing the non-closed orbits. So this whole schmuff of stuff gets collapsed to a point. But turns out that when you remove, so this is the bad stuff, and here I'm going to make an assertion and just not prove it. Let's just remove this. And of course, remember that the way I set things up, U is this guy here. So I'm simply taking, an open set. So here's my, good categorical quotient. I'm taking an open set, and I'm just looking at what's going on here. And it turns out that you can show that this is a geometric quotient. So what happens is that, this is almost a geometric quotient. Namely, you remove one bad point, and it's a geometric quotient, and then there's some basically bad stuff over that. And so that's the definition of almost geometric quotient. So that's where I'm going to end, is with basically definition 2. So we have a good categorical quotient, pi maps x to x mod g. We have two things that are equivalent. One is that there exists a G invariant open dense, I'll call it U naught contained in X, such that G dot X is closed in X for all X contained in U naught. So what that means is there's actually a big chunk of X where if I start in that, then I actually get something that's actually a closed set in the entire variety. It's not just closed in here, it's closed actually in all of X. And that's equivalent to the structure we had right here, that there exists an open dense set downstairs such that pi inverse of U to U is a geometric quotient. And the point is, this is almost geometric quotient. And what we're going to see tomorrow is basically the two key players tomorrow are going to be almost geometric quotients and geometric quotients. And so that's the actual quotients we have. So when you start this game, you sort of start at this sort of categorical level that gives you permission to have some pretty bad things. you'd like to have this, but in the real world, you get this. So for an example of an almost geometric quotient is this example right here. So what I've done right here proves that this guy is an almost geometric quotient. Okay, so that's it. Let's go drink beer or do whatever else you want to do to let the brains cool off. Thank you.